In this video, we're going to be looking at question 22 of the Unit 2 sample paper for the IAS Chemistry from Edexcel. So this question is focusing on the organic side of the unit, looking at specifically spectroscopy. So we have three compounds, A, B, and C, all of which have the same molecular formula, which is C4H10O. And we know that all of them are alcohols. And they give us the three infrared spectrum. So you can see that we've got compound A, compound B, and compound C. And we want to, for the first mark, identify one feature that is common to all three infrared spectra, which shows that all three are alcohols. Now, this is actually going to require you to look at your data book. And your data book should have this infrared spectroscopy page. And it gives you all of the different bonds and all of the different wave numbers. What is extremely important here when you're answering a question is you refer to the peak for the specific bond. Don't refer to it as a functional group. So for example, if it is an alcohol, the peak comes from the OH bond, not the OH group. So we want to focus on this section here where we have the alcohols and the phenols. If I just make it a little bit bigger, and you can see that we get a peak at approximately 3,750 wave numbers down to 3,200. So that's the most important part of an infrared spectra for an alcohol. So if we go back to our spectrums, you can see that between those wave number ranges, we've got peaks. So there is in compound C, there is in compound B, and there it is in compound A. So in order to answer this question, we should be saying what the peak is, give the wave number range, and what is formed by. So we have a peak at 3,750 to 3,200 wave numbers, and you just lift that straight from that data book, and this is for the OH bond. As I said, very important that you don't say the OH group, it is the OH bond. And now we want to look at, is there a way to identify each of these three different alcohols on the basis of just the infrared spectrum? Now, this is an unusual question in the fact that there are actually two possible answers, and the two answers contradict each other. You can either answer yes, or you can answer no. So we're going to look at the two different reasons. So if we say no, what we need to remember is that in the specification for Edexcel, we only focus on wave numbers above 1500. We don't look at anything below that because that is your bending peaks, and we don't look at them in the spectrum, and we call this part the fingerprint region. So if I just draw a line at 1500, we are focusing on everything on this side. Now we compare that compound C to compound B. Looks very, very similar. Compare that to compound A, again, looks very similar. So you can answer this question by saying no, because they all have the same peaks above 1500 wave numbers. However, a perfectly acceptable answer for this specification, that is actually something that's out with the spec, but something that you would have talked about in lessons, is you could use this part on the other side of the 1500 wave numbers down to 0, and we call this, as I said, the fingerprint region. So if you look at compound C and compare that to compound B and compare that to compound A, you can see they are all different. You can actually get a mark here for saying yes by using the fingerprint region. So two contradictory answers, but both of them actually perfectly acceptable. Moving on to part B, we are moving away from infrared and now focusing on mass spectra. And again, we are given the mass spectra of compound A, compound B, and compound C. So let's scroll to the question. We want to identify one feature that is common from all the mass spectrum, from A, B, and C, which shows the molecular formula is C4H10O. Well, that is going to be the same for every single spectrum, and you can see here, all of them have this very small peak at 74. And that peak is known as the molecular ion peak. So they all have the molecular ion peak at mass to charge ratio of 74, and that is for the C4H10O when the entire molecule has been ionized. And if you were to add up 4 times 12 plus the 10 plus the 16, you would get 74 as its relative formula mass. So that confirms that that is the correct molecular formula. For part 2, we're now starting to talk about the fragmentation patterns. And fragmentation questions can be quite tricky, and some people do struggle with these. So what we need to think about is the information that we're given in the question, and I would strongly recommend that you actually draw these out. So compound A, we are told, is butan-2-ol, compound B is butan-1-ol, and compound C is 2-methyl-propan-2-ol. So you're given some space down at the bottom, so the best thing to do is to draw them. So A was butan-2-ol, so that's your 4 carbons with your OH group on carbon number 2. Compound B was butan-1-ol, because remember, of course, these are all isomers. They all have that same molecular formula. And butan-1-ol has its OH group on carbon number 1. And then compound C, our tertiary alcohol, is 2-methyl-propan-2-ol. So we have our 3 carbons with a CH3 and an OH on the same middle carbon. And then, of course, always filling in all of your hydrogens. So now we have to look at how it's actually fragmenting. So we're going to take each one at a time. So for compound A, we have got a fragment causing a peak at mass to charge ratio of 45. So what you have to do is take your butan-2-ol and see where can I break it in order to get a mass to charge ratio of 45. And we assume that these are all 1 positive. So in reality, you're just breaking down the molecule and counting what has a mass of 45. And I can do that by breaking the middle 2 carbons and having this fragment here. The 2 carbons, the OH, and the other 4 hydrogens are going to give me a mass to charge ratio of 45. So once I want to actually write this out, I'm going to write the CH3, we have a CH and an OH, and we want to put the entire thing in brackets and put that positive charge. Because remember, all of these fragments are ionized, and this is where most people will lose their marks in a question like this, is forgetting the positive charge. For compound B, we have a fragment that is a mass to charge ratio of 31. So we do the same thing and we look, where could we possibly get 31? And the only place is by breaking the bond between carbon number 1 and carbon number 2, and that gives you the 12 of carbon, the 16 of the oxygen, and the 3 hydrogens, and that gives you a mass to charge ratio of 31. And again, when we write this out, we've got our CH2OH fragment, and we put in brackets with a positive charge. And for compound C, the mass to charge ratio is 59. So if our overall is 74, one of the most common fragments that can be made in any mass spectrometry is the methyl fragment, which is 15. So if we were to take the 74 and take away a methyl, which is 15, that leaves me with 59. So in reality, what's happening is all of this part is being left over, and we are breaking the 2 carbon bonds. So again, I have to write this out. And how do I do this? Well, I've got my carbon with the OH group attached to it, and then I have 2 CH3s attached. So I can put the CH3 into brackets with a 2 outside, and then the positive charge. Or you can write this as CH3, C, CH3, OH. Both of these mean exactly the same thing. So when it comes to a fragmentation or a mass spectrometry question, I would always recommend drawing out your structures. You will find these questions so much easier if you have the structure in front of you and you can then start to break the bonds and figure out what each of the fragments would be. For question C, we are looking at the identification of compounds A and B. So we know that these are alcohols, we've been told this, and we want to mix them in order to be able to determine which is which, and we're mixing them with potassium dichromate and dilute sulfuric acid and then distilling. And we want to identify by name and structural formula the organic compound that is present in both of these. So for A, we know is butan-2-ol from our mass spectrometer, and for B, we know is butan-1-ol. And we have to look to see what is being oxidized. Now, very important, one thing to take from the question is this part, that we are distilling the mixture immediately. That means that we only have a 1-step oxidation. Because if you remember, a primary alcohol can undergo 2-step oxidation to get to the carboxylic acid. Here, we're only allowing partial oxidation. So we should have the alcohol either going to an aldehyde or to a ketone. And we must make sure that we get them the right way round. The aldehyde comes from the primary alcohol and the ketone comes from the secondary. So now we can name the two. So butan-2-ol is a secondary alcohol. Therefore, that must be making the ketone. So we call that butan, and we remove the 2 and the OL, and we add ONE. So this is butanone. And this has that structural formula of CH3, CH2, the carbonyl, and then a CH3. So remember, for a ketone, the carbonyl is in the centre. If you struggle with structural formula, what you might find useful is, again, draw out the molecule. So you could potentially come up to the top, or on a scrap piece of paper, if you ask your teacher or your exam officer, you can draw out the ketone and then convert it into your structural formula. For the butan-1-ol, we know that this is a primary alcohol, so we're making the aldehyde. And again, I do the same thing where I remove the 1 and the OL, and I call this one butanal. And again, I can draw out the structural formula, draw the full displayed, and this time the carbonyl must be at the very end of the chain, like that. And that will allow me to draw out my structural formula in the shortened. So I've got CH3, CH2, CH2, CHO. You will get 1 mark for each of the structures and the 3rd mark for the 2 names. And then to identify A and B, the student decided that one further chemical test could be used on their oxidation products. So this is just another way. We've done infrared, we've done mass spectrometry, we're doing oxidation, and these are all different chemical analysis to confirm the identity of A and B. So we want to give a suitable reagent and the expected observations that could distinguish between the oxidation products of A and B. So you want to look at how do you distinguish between an aldehyde and a ketone. You will get 1 mark for identifying the reagent and 1 mark each for saying what happens with the aldehyde and the ketone. And there are 2 key substances that you can use here. So the first one is Benedict's reagent or Fehling's solution. both of them are acceptable answers and we see the same thing. So for our aldehyde, we see that colour change where we go from a blue solution to a red precipitate. It's extremely important when you're talking about Benedict's solution that you use the term precipitate. You cannot just simply say blue to red. You must specify that it makes a precipitate. Whereas with a ketone, we get no further oxidation because these are oxidation substances that will allow you to then go to the next step in oxidation. And our ketone therefore cannot, and we get no colour change. The alternative answer is using Tollin's reagent. A slightly more unusual oxidizing agent, but does still give you a result that can distinguish between the two. So the aldehyde gives you that lovely silver mirror because we get the silver in the Tollin's reagent being reduced back to silver metal. So we get a silver mirror being formed. Whereas with the ketone, same as the Benedict's, we see no colour change. And that's a way to determine if you have an aldehyde or a ketone. Again, 3 marks, 1 for your oxidizing agent, 1 for your aldehyde, and 1 for your ketone. Now that's 12 marks covering the alcohols and their oxidation, mass spectrometry, and infrared. So a nice well-rounded organic question. If you have any questions on this, please feel free to leave a comment below and check back on the playlist for the remaining section of this paper, which covers the synoptic question.